Good evening everyone. My name is Renu Raman Sahu and welcome to today's course on Plasmonics Fundamentals and Applications. So in the last class we had discussed about different frequencies, the response of the material to different frequencies of the driving field, of the electromagnetic field. So we had discussed up to what would happen if the frequencies are very low frequencies till up to the plasma frequency. When the frequency is less than the collisional frequency, what would happen? We discussed that it will be in the material will or the metal will absorb, and in the frequency where if the frequency of the driving field is more than the collisional frequency, then the metal will mostly reflect. And that is why the position of this plasma frequency is really important for the metal to behave as a metal that we all know conventionally. The frequency of the driving field, it has to be less than the plasma frequency. Okay, for example, some material whose plasma frequency is in the UV region, then we can use its plasmonic properties for all the ranges from up to very low frequency till and encompass the entire visible region. Okay, so today what we are going to do, we are going to do the frequency analysis, but at frequencies, at the plasma frequency, how the material will behave, and at the frequency more than that, the plasma frequency. So let us get started. So what we discussed in the last class was just a small recap. If so, we talked about different frequency regime analysis. There was the plasma frequency omega p, there was the collisional frequency. At low frequency, by low frequency what we mean? Low frequencies from this to this. If omega is in this region, metal is mostly absorbing. And we had derived the relation between permittivity and the conductivity and linked it with the Drude model. So at low frequencies, epsilon or the permittivity, we had derived that it was 1 minus I sigma omega over epsilon naught omega. This is at low frequencies. At high frequencies, what would happen? At high frequencies, and what do we mean by high frequency? High frequency is somewhere close to the omega p, but still less than omega p. So in this region, metals are mostly reflecting, and this region, it turns out that this frequency region is almost the visible region. That is why you see most of the metals are very lustrous and shiny. Okay, this was what we did in the last class. We also had we also had connected the Drude model to the plasma model. And today what we are going to do, we will be talking about the and one more thing we did was that what would happen, how do we model a real metal. Real metal, it has the electrons in this metal are from usually particularly from, for example, silver, gold and copper. Electrons, free electrons, are mostly from S cell, and that is why what would happen is these electrons from S cell see a polarized background. Because all the P cell, S cell, D cell, and usually it is the D cell, and because of that the permittivity we had this, instead of this epsilon infinity, instead of it as a 1, which is true for the uh, just a pure plasma, we had this expression. This is the expression of the permittivity. Now what we are going to do today, let us move ahead to the new topic. And today what we are going to do, so all these things, they were in the frequency regime where omega p is some frequency here, and all this analysis that we discussed in the last class was in the frequencies less than the plasma frequency. This was till the previous classes. In today's class, what we are going to do, we are going to see what happens at plasma frequency and frequencies. So this omega is the frequency of the driving field, where omega equal to frequency of driving field. So so this topic is, what happens is, one, the dispersion of the free electron gas and the volume plasma. Now let us consider that the frequency omega is greater than or equal to omega p, where omega p is the plasma frequency. Now in this regime we know that the permittivity epsilon omega is somewhat 1 minus omega p square over omega square. Okay, and we had defined something called the wave vector denoted by k square, and it was related as epsilon k omega square over c square. Okay, now what we will do, and usually the diagram of frequency would look somewhat like this. 0 gamma is somewhere here, omega p, and the frequencies we are talking about are greater than the plasma frequency. Okay, now let us try to derive what is the, so we have this relationship here, k square equal to epsilon k omega square over c square. From here we can get the omega square as k square c square epsilon of k and omega. Okay, now this epsilon we know from this expression 1 minus omega p square by c square. Let us just put that. So k square c square this is divided by, Now what we are going to do, we'll start from here. This is what we had derived here at the bottom, and instead of epsilon what we are going to write, omega square omega 1 minus omega p square over omega square. Okay, so this on simplification is omega square minus omega p square. Okay, so from here what we get is omega square is equal to omega p square. Omega p is the plasma frequency, which is the property of the material, plus k square c square, where omega p is equal to n e square open m epsilon naught and the square root of that. So this is the relation between omega and k. K is the wave vector, omega is the frequency, and what we obtain here is called the dispersion relation. We can simplify and write as omega over omega p just to make it non-dimensional. Kc over omega p whole square. Now if you plot omega versus k, how it would look like? So we obtain the dispersion relation, omega over omega p whole square is equal to 1 plus kc over omega p whole square. So this quantity kc over omega p is a non-zero quantity and it is added to 1. So that implies that omega is greater than omega p. Then only this condition can be satisfied. If you plot omega over omega p, and this axis is omega p over omega, and here kc over omega p, and you take this as 1, and this line is called a light line because this corresponds to omega equals kc, or this line is called a light line. So what we obtain here is that at when k is 0, omega by omega p is somewhat equal to 1. So it starts from 1. And when k is too large, we can neglect 1. When k is too large, it should coincide with this omega equals kc wala line. So what we have is it will increase and keep on increasing till it becomes tangential to this line. So this is how this particular dispersion relation looks like. It starts from 1 and it goes along the light line. So what is happening here? So at omega less than omega p, the propagation of transverse EM waves was forbidden inside that metal. So it was either absorbed or reflected back. So the propagation of transverse EM waves is forbidden it is forbidden inside the metal plasma. Now, but as omega by omega p approaches 1 and then beyond, what we obtain is the plasma will support the transverse waves propagating with some group velocity. And they propagate with a group velocity. So what we can do, we are going to take the derivative of the expression that we got, omega square is equal to k square c square and what we are going to do, 2 omega d omega by dk is equal to 2 k c square so this implies that d omega by dk and omega we can write as omega p square plus k square c square, and if you divide, what we'll get is this quantity is of course less than c. Why it is less than c? It is because the denominator is greater than 1 and both numerator and denominator are positive in nature. So now what we got is that the plasma can support transverse waves propagating with a group velocity, which is given by this c upon omega p over kc whole square plus 1. Now what we are going to do is, we will note that what would happen in the very small damping limit. In the very small damping limit, note that in the small damping limit, that is the imaginary part of the permittivity is much smaller than the real part of permittivity, we have epsilon omega is equal to just the real part 1 minus omega p square open omega square, and epsilon of omega p, this corresponds to 1 minus omega p square upon omega p square, that is 1 minus 1 equal to 0. So the plasma frequency is the root of it is the root of epsilon omega p is equal to 0. So what it means is that since we have at plasma frequencies we know the relation that k square is equal to epsilon k omega square upon c square. What this corresponds to is at omega p, k square is equal to, so at omega p, epsilon k omega p square over c square. So at omega p this epsilon is 0. Okay, that is why you have k is equal to 0. What does this mean? So k is 1 over lambda, like with some factor 2 pi or something, it is 1 over lambda. That means lambda has to be infinite. So and what is lambda? Lambda is the wavelength of the oscillation of the plasmons, and lambda is infinite means the wavelength of the oscillation is infinite. That means there is no variation in the oscillation of electrons along the direction of so along the depth of the material or along the k vector direction. So what we can say is that this is the collective oscillation of the electrons. So k is equal to 0 implies that this excitation corresponds to a collective longitudinal mode. To just for the sake of visualization, if we have a very small length, let's say this and this, and the k vector is along this direction, and let us say suppose this is the wave vector, this is how it looks like. That means the electrons here are oscillating like this, here it is oscillating like this, and the amplitude is increasing up to this point, and then the electrons are oscillating in the opposite direction. Now if we have, so this corresponds to this is how the electrons are oscillating for this particular wave vector. Now for this wave vector, so this is the thin strip of metal of thickness t, let's say. For this, suppose if the k vector is this, that means all the electrons are oscillating in the same direction, but with the profile of the amplitude given by this k vector. Now if we have a very long wavelength, so when we say infinite, it means very long wavelength with respect to the even the thickness of the material. So if we have let us say this is the zero line and we have a very long wavelength, that means all the electrons are oscillating about the same amplitude and in the same direction. And when this becomes negative, all the with time, when this will become negative, all the electrons will be oscillating in this direction. So it is all the, since all the electrons are oscillating in unison, it is called a collective oscillation. And why longitudinal? Because it is in the direction of the k vector. Okay, so in this case, so this corresponds to this case. In this case, the D vector, which is nothing but epsilon naught epsilon E, is equal to 0, since epsilon is equal to 0 at omega equal to omega p. Now what does this mean? What is epsilon naught? What is D vector? D vector is epsilon naught E plus p. That means the electric field E is totally given by your polarization. Or since it is minus p, it is called a depolarization field. So at plasma frequency, the electric field is pure depolarization field. What is the physical significance of the excitation at omega p? So now consider the collective longitudinal oscillation of the conduction electron gas. Versus the fixed positive background of ion cores. So what we are doing here is we are considering a slab, let's say this one for the sake of picture. This is the slab, and let us say that electrons, so this is the slab, there is a positive background and there is an electron plasma. So let us first assume that this is our first assumption. So we are saying that the electron cloud, it is collectively displaced by a distance u. So what happened is, for this particular slab, this got negative charges here at this surface, and here there are positive charges. So the electrons moved upward by a distance, very small distance u. So what is the surface charge density now? The surface charge density is, let's say, sigma is the sigma, it will be given by minus n is the number density of electron, and this is the electronic charge, and u is the displacement of the electrons along u is the displacement of the electrons from the positive ionic cores. So n is the number density. So this is the per volume. So this is the unit. If you see, n has a dimension of 1 by L cube, and u has a dimension of L, or the length, and E has the density of charge. It has the unit of charge. So if you see sigma, it is L minus 2. This is the dimension of sigma, which is nothing but surface charge density, or the charge per unit area. So sigma is given by minus NEQ on one side of the plate and plus NEU. So we'll just write this, sigma plus NEU. So this is the surface charge density. So now this is like a capacitor. Okay, the surface charge density at the slab boundaries would be So now what happens because of this surface charge boundaries is that so this is like a capacitor, and the electric field due to the electric field inside of these plates would be, so electric field E. So this is homogeneous. So this surface charge density, so this establishes a homogeneous electric field. Of magnitude would be E is equal to sigma upon epsilon naught. It is nothing but NEU upon epsilon naught. Now the displaced electron will now experience a restoring force, because now this is the electric field. Now this electric field will because of this electric field, so electrons in the presence of this electric field will presence a force. Okay, so the displaced electron will experience a restoring force and that force is given by, let's say, m is the mass of electron, and u is the acceleration, and this is just the Newton's second law, minus E times the electric field, and we had the electric field as n E u upon epsilon naught. So this is nothing but minus n E square u upon epsilon naught. So what we have here is u double dot, or the time derivative, double time derivative, minus n E square upon m epsilon naught times u. So what we have here is u double dot plus n E square upon m epsilon naught u is equal to 0. Now this is the differential equation for a harmonic oscillator, where this is the frequency of the oscillation. So this you can write as u double dot plus omega p square u is equal to 0, where omega p is nothing but n E square upon m epsilon naught to the power 1 by 2. So this plasma frequency, so this is what we had recognized in the previous derivation, where we had written that epsilon omega p is equal to 0, that implies k is equal to 0, and that corresponded to a collective oscillation. Here we can see pictorially that when we displace the electrons by a small distance u and calculate how the electrons will behave, it also behaves as an oscillation. Now since we had taken any single arbitrary electron in that plasma, it applies for all the electrons which is in between that electric field. So the plasma frequency omega p, it can be thus recognized as the plasma frequency omega p can thus be recognized as a natural frequency of free electron oscillation of the electrons here. So we note that all the electrons are moving in phase here, and this corresponds to k is equal to 0, and the quanta of these oscillations are called plasmons. So what are plasmons? The plasmons are collective oscillations and are, so these are also called volume plasmons. Now, due to the longitudinal nature of this excitation, this cannot be excited by the electromagnetic waves. Okay, because electromagnetic waves are transverse in nature. So how this can be excited? It is only by if you hit some particle with particle longitudinally. For example, if you hit electrons into a thin metal foil, then it can excite the volume plasmon in there. So due to the longitudinal and their decay. So once this oscillations are created, so now they will be decayed, and this decay will occur only by the energy transfer to a single electron, and this happens by a process called Landau damping. So how do we actually experimentally see this volume plasmons or this plasma frequency? How can it be experimentally measured? So they can be measured by something called an electron energy loss spectroscopy. It is also called yields, and in this technique, electrons are passed through the very thin metallic foils. For most of the metals, this plasma frequency it is in the UV range. For most of which is around 5 to 15 electron volt of energy, and it depends on the band structure where in this particular band it will lie. So this is about the metal, but note that this kind of longitudinal oscillations can also be excited in dielectric, and in this case the valence electrons oscillate collectively with respect to the ion cores. Okay, because that valence electrons are it is in the field state. The in-plane oscillation is one particular type of, it is a very one particular type of longitudinal oscillation. Okay, but there can be other oscillations which can be longitudinal but k is not equal to 0. But there can be oscillations in which k is non-zero. I mean, the cases for which so here we will not much go into the derivation of the derivation of the dispersion relation of volume plasma. So we'll just write it here. So this can be found in many condensed matter physics books. And it is usually given by omega square is equal to omega p square plus 2 EF is the Fermi energy, K is the wave factor, and M is the mass of the electron. And this is true up to second order in K. And practically with yields one can measure this dispersion relation. Where yields is the electron energy loss spectroscopy. Now how does the real metal behave? The real metal in the sense the gold, silver, so they have something called an interband transitions. So the Drude model can accurately describe the optical response of metals only for photon energies that is below the these transitions and this transition between this electronic bands. Okay, so that is the first point to note for the Drude model. Okay, so just note it down. Okay, so Drude model works only for the photon energies which is below this threshold between this electronic bands. And some noble metals they have the interband effects, they start to occur from 1 electron volt already. Okay, for example, for the gold the Drude model fails to explain the dielectric function near the visible to NIR region. Now when we consider this gold and silver for most of the, like we will consider gold and silver for most of the discussions because gold and silver are the usually known plasmonic material and most widely used, but they have this interband transition and they cause a lot of they cause a lot of experimental mismatches. So for some noble metal, for example gold, near the visible to the UV region. For gold, this grid model doesn't work because of this intermittent transition in gold. So let us consider gold and silver for most of the discussions now. So above the band edge thresholds, the photons are efficient in inducing the interband transition. For example, if this is the band, this is the band edge, this is the valency band, this is the conductive band, and the photon, it has an energy greater than h nu greater than this band gap. So this energy is Eg. These photons are efficient in inducing the interband transition. These photons are and the consequence of this is that the now since the photons are now being used for the interband transition, these photons cannot couple with the surface plasmon polar return. So as a consequence, the surface plasmon polar return, this will be damped more. And this is because there is a competition between the surface plasmon excitation and the interband transition. So what is happening is that, let us say that suppose this is a metal, and metal has this interband transition. When the surface plasmon, suppose here the surface plasmon polar return is excited, so there are electrons here, electrons. Assume that this is the ion core is made of this metal chunk. These electrons oscillate. They oscillate in the presence of the light. So surface plasmon polar return will be these electrons will oscillate, and the oscillation of these electrons will give out photon of energy h nu. Now these photons will have a wavelength will have an electric field, and because of this photon the electrons will get again oscillation. Now when some of a flux, let us say that this is emitting some photons and they are propagating in certain direction. These photons are propagating in one direction, and along with that along the surface the electrons are also oscillating. Now some of these photons, so as long as these photons are not getting damped or not getting wasted into some other process, then these photons can be used to oscillate the electrons nearby, and therefore that coupling between these photons and electrons in the surface plasmon polar return will be efficient. Now if some of these photons are now used for this interband transition, now less amount of electrons can be oscillated by the available electric field because the number of photons are less. So hence the there is this competition between SPP versus intermittent, and that leads to quicker damping of SPP. Now the next question is, how do we take this intermittent transition into account? So for practical purposes, the Drude model can be easily incorporated into some time domain based numerical solvers, okay, like FDTD, okay. And Drude model, so it is important to have some correction to the Drude model so that it can take into account this intermittent transition. So Drude model can be, so like this, for example, one numerical scheme is FDTD, which is finite difference time domain, and one commercial package is numerical, which is mostly used in research. There are others, but numerical is one of the mostly used. So it is important to overcome this inadequacy of Drude model, and that can be achieved by incorporating another term, so this was our usual Drude model equation, and we'll add another term to take into account the intermittent transition, that is so this term takes into account the intermittent transition, and this is illustrated by using a classical picture of a bound electron with some resonance frequency omega naught. Note that a number of equations for this of this form might be required. Like for example, this is just one equation, but a number of equation like a multiple equation like having gamma 1, gamma 2, gamma 3, they might be used to uh, might have to be solved, and each resulting in a separate contribution to the total polarization in order for the total epsilon omega for noble metals accurately. Okay, so like to be precise, where this omega I is similar to this omega naught, gamma I is the damping constant, and ai is that oscillator strength. So when this is incorporated, now we will have a change of the permittivity as well. So we have the equation M. Now if we take this answers of harmonic oscillation, that is x equal to x naught e to the power minus I omega t, So x dot will be minus I omega x naught e to the power minus I omega t, which is nothing but minus I omega x, and x double dot is equal to minus I omega whole square x naught e to the power minus I omega t, which is nothing but minus omega square x. Now this will lead to what? Minus m omega square plus omega square x minus I gamma omega x plus m omega naught square x is equal to minus e. This gives us minus m omega square minus I gamma omega plus m omega naught square. There is an m missing here. I m x is equal to minus e. This implies that x is equal to minus e over minus m omega square minus I m gamma omega plus m omega naught square. This gives us the polarization P is equal to minus NEX, which is nothing but minus NE minus EE upon X. We are using it from here, minus M omega square minus I m gamma omega plus m omega naught square. Is equal to n e square e upon m epsilon naught if we take common. So what I am doing is multiplying an epsilon naught up, and m I am taking common, and epsilon naught from the numerator. So it is omega naught square minus omega square minus I gamma omega. So what we have here now is that the dielectric field D is equal to epsilon naught E plus P. So epsilon naught E plus P is equal to n E square upon m epsilon naught, and epsilon naught E divided by omega naught square minus omega square minus I gamma omega. That implies epsilon naught E. So epsilon naught, then we will take this common 1 plus n E square upon m epsilon naught divided by omega naught square minus omega square minus I gamma omega times E. And D we know that it is epsilon naught epsilon E. This implies that epsilon, which is a function of omega of course, is nothing but 1 plus, and n E square upon m epsilon naught is nothing but your omega p. Omega p square omega naught square minus omega square minus I gamma omega. and we can write this part as this part in the bracket as omega p square, which is nothing but n e square over m epsilon naught. This is what we have here, and this is the dielectric function in the presence of interband transition. Now let us spend a bit of time on the energy of the electromagnetic fields inside the metal. So for a linear medium with no dispersion or losses, a linear medium with no dispersion or losses, the energy density of the electromagnetic field, the energy density it is given by this U equal to half of E dot D plus B dot H. This can be found in any standard electromagnetic book, for example the Z Jackson, okay. So this is the energy density. Now the conservation of energy will dictate that the change of energy density has to be balanced by the flow of energy density, flow of energy into or out of the system. So the change of energy density, this is a kind of continuity equation, divergence of S, where S is the k vector or the Poynting vector, that is equal to minus J dot E. E is the electric field. And what is this? This is the electromagnetic work done on the system, where S is nothing but your Poynting vector. Poynting vector is given by E cross H. Now let us concentrate on the contribution of the, so now see there are two components here, the electric component and the magnetic component. So here this is the UE and this is the UM, the magnetic component. Okay, so let us now focus on the electric component of the field. So what we want to find out is the what is the contribution of UE to U, or what fraction of U is the UE. So in metals, this epsilon or the permittivity is complex, and it is a frequency dependent due to its dispersion. Therefore this relation doesn't apply for metal. So in metals, epsilon, it is complex and frequency dependent. Now why it is due to the dispersion? Therefore U is equal to half E dot D plus B dot H. This relation does not apply for metal. Okay, because of these two reasons. It is complex and it is frequency dependent. Now, for a field consisting of a monochromatic components, the Landau and Lipschitz have shown that this conservation law can be hold if okay, in metal, for a monochromatic so this conservation law what is the conservation law? It is nothing but this. This can be held up if the UE is replaced by the energy density U effective, which is nothing but half times real part of this d omega epsilon over d omega at omega naught, okay, times the dot product of electric field. So what it is done? It is the E square and it is the time average of that. It is the spatial average of that, and it is this electric field is appreciable only in a narrow frequency range around omega naught, because here we are calculating only here at omega naught. This is nothing but the spatial average or the field average over one optical cycle. And this is valid only if E is appreciable in a narrow frequency range So that is, this E is varying slower than this time omega naught, and epsilon 2, these are the conditions for which this expression of energy density is applicable. This is less absorption. The right hand side is also replaced by, if the metal is completely described by epsilon of omega, then the right hand side of this expression of what is the right hand side? E j dot E, that is, this j dot E is replaced by omega naught imaginary part of epsilon omega naught times the field average of and the expression of the dielectric field is the expression of electric field energy described by a free electron type dielectric function that is epsilon equal to epsilon 1 plus I epsilon 2 is given by, that means epsilon omega is equal to 1 minus omega p square upon omega square plus I gamma omega. It is given by this expression, and the expression is given by U effective is equal to 1 by 4 epsilon naught epsilon 1 plus 2 omega epsilon 2 over gamma times mod E square. So this is the energy density of due to the electric field inside a metal. So this we will just take it for granted now. We will not go into the derivation, but this is the if the metal is described by this free electron model, then this is the energy density. Due to electric field. So to summarize, what we did today is we looked into the different oscillations. We looked into the different longitudinal oscillations and showed that at omega is equal to the plasma frequency, we have this longitudinal oscillations, and this can be experimentally determined by something called the electron energy loss spectroscopy. And then we went on to describe the uh, energy of the electrons. And then we went to see the physical significance of this omega p by considering a slab, and then we displaced the whole of the electrons collectively and saw that it actually corresponds to k equal to 0 limit. Then we went on to describe what is the electric field, what is the energy density due to the electric field inside the metal, and we came up with this expression which you can see right here, right now. In the next class, what we are going to do, that we were going to describe the surface plasmon polaritons at a metal insulator interface. So we will start with the Maxwell equations, and then we will see how the dispersion relation of this surface plasmon polariton will come out. So thank you.